So in our electrical systems section module, we're required to know some terms. Many of these we can't practice out in our lab, like we were in some of the former modules. But we do need to connect these um, to learning so that we are competent when we discuss things in project planning with contractors and engineers and other people who are involved in our project. So some of the terms we're going to be required to know: amps, volts, ohms. You may already be familiar with these from high school physics. The idea of generators and motors, transformers, step up and step down. The idea of difference between AC power and DC power. And then we're going to actually look at some of the physical devices that we see in a construction site, panels, circuit breakers, etc. This is the project that we're actually going to do for this associated section. We placed some lighting fixtures. This is a really nice project done by another student last year. So we have the idea of placing lighting fixtures, how it gets illustrated and indicated, the code required placement of electrical outlet fixtures in our kitchen break area, etc. And oops, no, what happened to that there? So that's just another project, nice project, and another nice project. So hopefully that'll set the bar for you. Um, Electrical power really seems important when you don't have it. In California last year, there were massive power outages because of fires on supply, utility grid supply, making us rethink the value and importance of our electricity, especially when we need it for human comfort and survival, things like air conditioning. We also, on a really small scale, we need to understand these electrical terms when we come to this idea of device selection. I have this highlighted in red over here only because this is about mounting heights, and I found this very unusual. We talk about ADA requirements, so they talk about it being 45 inches for a man, 43 for a woman, and 37 to be accessible. It seems like they all should be at 37, but I'm kind of at a loss to understand why they made that standard. That's a bit of a distraction, though. The important thing about electricity here is that you should be able to look at a chart like this one for electrical supply, understand the voltages that are being stated and what their implications are for planning and specifying on your drawings, how much amps it requires, what that means as far as significance, and maybe some of the things that aren't necessarily important, like once you supply these, this tells you how much energy is required to consume, so you can tell if one's more efficient by the amount of wattage, but it isn't a requirement to necessarily be on a drawing. Um, and then this last one I think is really important, and this is code approval. So this is UL Underwriters Laboratory, and the one down here is the Canadian standard. These are codes. When a device has one of these stamps on them or approval, it means that it's an industry standard for acceptability and safety. Without one of these stamps, it would be likely that you wouldn't want to install that appliance, or an electrician would not want to install it. So we're always looking for these code approvals, especially when we're looking at new equipment or unusual equipment that we might want to specify. Here's just a general statement, once again, about that idea of how important electrical power is to our architectural work, and the need for the basic understanding of the principles. So one of the easiest ways to think about electricity that we kind of have a handle on is this idea of water pressure. So we have the amount of flow being the current, and the amount of pressure being kind of the voltage. And you might want to just pause and look through this to kind of take it all in. I want to move a little quicker through it, and then you can come back to this. Um, it's important, and we're going to come back to that in some detail. I just wanted to introduce a couple of other terms. The idea of direct current, alternating current, single phase, and three phase. Um, we deal at the outlets always with alternating current. The only time we really deal with direct current is when we're talking about things that are battery powered or have what you would call these wall warts or power supplies, things that plug into the wall and then plug into something like a computer. The output from them is typically direct current. For us as architects, it's very seldom that we need to deal with direct current. The only other place I can think of is with power supplies coming off of solar panels. that's always a DC current and it needs to be converted for home use. So I wanted to show you this idea right away of what alternating current is. So here we have a graphic down here. This is single phase over here. So it's typically we have what's called a peak to peak voltage of 110 volts or 120 volts and single phase. But in more advanced systems, in commercial buildings, for power distribution, for supplies to large air conditioning systems, we have what's called three-phase power. So there are multiple wires supplying three different phases of electrical current. And the reason why this is very popular, three-phase power is popular in commercial applications, is that it reduces the sizes of the wires that are required because it's a more efficient way to deliver electrical energy to create power in motor systems. So when we talk about the difference between most of our home and residential construction, we'll deal with single phase power, and a lot of our commercial work will be based on the idea of bringing in three-phase power. And once we have three-phase power and we still have the same kinds of availability that we would for residential single phase, because we can always just tap off one of these phases to get a single phase supply for appliance and or distribution. So we've talked about this idea of voltage and current, the idea of the amount of flow of water and the pressure of water, in this case, the amount of flow of electricity and the amount of force to drive it. And that's really understood only when you're pushing the force, when you're pushing it through a resistance. That resistance could be a motor, it could be a heater, it could be a light bulb. And the relationship between all of those is the current is equal to the voltage divided by the resistance. Now, this formula is a requirement for understanding, but in most practices, you will not need it. We usually do not know what the internal resistance is of many of the appliances we use, and we're giving the current demands and the voltage demands directly specified by the vendor, contractor, or written on the appliance itself. So while it's important as a standard for you to know this, I don't see much time for you to use this in practice. Something that's more important to understand is this idea of wattage, the amount of energy that we actually consume. So here I pulled off that little tag strip from the air heater, the hand dryer, and I want to like punch up this idea that wattage is really the amount of energy that we're consuming, and it's the product of the current and the voltage. So we have, if you were to take any of these numbers here, if you take 110 volts by 11 amps, 11.3 amps, you would come up with these nominal, if you multiply these two numbers together, you would come up with these kind of wattage values. So here we have 6 times 230, so we know that's 12 plus 2, so it's around 1400 watts if you just did the math of 230 times 6.1. So this formula, wattage equals to V times I think is really important. That helps you to understand, because if you're given the amps and the voltage, you'll know how much wattage a device will consume, and then you can compare one device to the next to determine which one is operating more efficiently. And I'll take a break there and then we'll come back in the next section.